And we have a very fun and exciting problem in section 5.3, problem number 87 on page 146. I encourage you, before watching the solution to this problem, attempt to work it on your own. We have an 8 kilogram block attached by a string through a pulley here to a 16 kilogram block. The 8 kilogram block is resting on a inclined plane. It has a degree of incline of 37.0 degrees. There is friction between the 8 kilogram block and the surface of the incline. The coefficient of friction associated with those two surfaces is 0.23. We're asked to find two things: the acceleration of this system of two blocks and the tension that must be in the string. To find the acceleration, our first thought should be net force. What are the forces that are acting on this system? Before we can look at the net force, we need to know what those forces are using a free body diagram. This dot represents my 8 kilogram block here. We have the normal force that's pointed perpendicular to the surface. And then we have the weight force, or the force of gravity on the object, which we call weight. There's weight. And then we also have a frictional force that is pointed down the incline, or opposing the block's motion up the incline. There's our force due to friction. Those are the three forces acting on our object. If we rotate our axes so that the x-axis is this incline and the y-axis is the perpendicular plane to the incline, that makes this normal force along the y-axis, this frictional force along the x-axis in the negative direction. This weight will have to be split into two components. One y component of the weight, and then an x component of the weight. The angle between the y component and the resultant weight is the same as the angle of this incline, 37 degrees. All right, let's look at the forces that are acting on the system now that we have these identified as frictional force acting on the block, which we need to show the normal force because that ties into our frictional force. We're looking in particular here the forces acting in the x direction, and that is what is causing our acceleration in the x direction now that we've tilted our axes. There's one force I neglected, and that is this force pulling the block up the incline, and that is the force of block B. We'll call that force 2. So we have the force of block B, force 2, that's pulling us up the incline. We have the kinetic frictional force that's also acting in the x dimension. And finally, we have the x component of the weight that's acting in the x dimension. We have these two that are opposing the motion of the block up the incline, frictional force, and the weight, both trying to send the block down the incline. There's one force that's pulling the block up the incline, and that's force 2. We know that the sum of all of these forces in the x dimension equal the mass times the acceleration of the object in the x dimension. Force 2 is active in the positive direction. The frictional force is in the negative direction. The weight is also in the negative direction, the x component of the weight. Together, those three forces give us the magnitude of the acceleration in the x dimension. All right, there's a bit of math that we have to do here that we'll come back to in a moment. once we analyze the y dimension. Let's take a look at what's happening in the y dimension. The forces that are acting on our 8 kilogram block in the y dimension are the normal force, perpendicular to the surface, as well as weight in y, or the y component of the weight. That again equals the mass times the acceleration of the block now in the y dimension, because these are the forces in the y dimension. The sum of these forces is equal to 0 because there is no acceleration in the y dimension. So 0 times mass gives us 0. The normal force is in the positive direction of y. The y component of the weight is in the negative direction. We can conclude, therefore, that the y component of the weight is equivalent to the normal force. This is important because we're going to need this information to put it back into this frictional force. So let's start analyzing the forces here. F2, that is the force that the 16 kilogram block applies to the 8 kilogram block. What is that force? That force is due entirely to the weight of this 16 kilogram block. In other words, this pull, this F2 that's acting on the block, on the 8 kilogram block, is due entirely to the weight of the 16 kilogram block. So looking back here, we can put in the mass of the 16 kilogram block times gravitational field that it's in. That gives us the weight of the block. The frictional force, we'll need to use the normal force and the coefficient of friction to find that. And then here we'll use trigonometry to find the weight in the x dimension, or the weight of the block, of the 8 kilogram block, that's still pulling it down the ramp, that causes it to, or tries to pull it down the ramp. Filling in this first force 2, we find that force 2 can be rewritten as mass of the larger block times gravity. The frictional force here we can rewrite as minus the normal force times the coefficient of kinetic friction. In weight in x, we can rewrite that as, well, looking over here, how are we going to find weight in x? We know the weight of the 8 kilogram block. We know this angle. This side, this vector component, is opposite this angle. If we use opposite and hypotenuse, we know the hypotenuse. When trying to find the opposite, we can find the x component of the weight. It'll be the hypotenuse, which is our weight, little m times g, because that's the mass of our 8 kilogram block, given that this weight component, or this weight, represents the weight of the 8 kilogram block. Little m times the gravitational field, that gives us the total weight, but we only have part of the total weight that's opposing our motion. We use sine to represent that, sine of 37 degrees. And that gives us mass times the magnitude of our acceleration in the x dimension. Right, so the only trick I did here was say that if I take the sine of 37 degrees, sine of 37, I'll write that in the space right here. The sine of 37 degrees equals opposite, so weight in x, over hypotenuse. So the weight, we know we find the magnitude of the weight by m times g. Solving this equation for the weight in x so that I can replace it here, I just multiply each side by mass times gravity. So I get mg, little m times g, sine of 37. We'll do similar trigonometry whenever we do a bit more analysis here on the normal force. The large mass times gravity, that stays the same. The normal force we know is weight in y, all right? What is weight in y? We use similar trigonometry that we used here, except this time we'll use cosine because we have an adjacent angle, or adjacent side, adjacent component to this angle. Cosine of 37 degrees equals the y component of the weight, because that is the adjacent side. Cosine is adjacent over hypotenuse, again, little m times g. If we solve this, we see mg times cosine of 37 gives us the y component of the weight. We know that the y component of the weight is equal to the normal force. So instead of putting normal force, I can put mg, little m times g, times the cosine of 37 degrees. Still times mu sub k, the coefficient of kinetic friction. This whole term right here is my the frictional force that's acting against this 8 kilogram block. That's represented here. That force right there, the frictional force, depends on this normal force, which we know is equal to the weight in y. And then we can write this last term here, nothing new that we need to write for mg sine of 37 degrees. Equals, now this m right here, this has been suspicious for us. That m should represent the mass of the entire system, not just the mass of the 8 kilogram block or the 16 kilogram block. These forces are the forces that are acting on the whole system. So what we should write instead of just m is capital M plus little m. That would be the mass of our entire system. If you remember our Robin Hood problem, this is very similar to the Robin Hood problem, except now we have an object that's on an incline and we have a frictional force to consider. Otherwise, it's conceptually very similar. Here's the total mass of our system times the acceleration of that system. Last thing we need to do is divide by the sum of these two masses, or the total mass of our system. And now we have found the acceleration of our object. This large m stands for the larger mass, so 16.0 kilograms. The g we see in each of these terms is the gravitational field, 9.80 newtons per kilogram. The little m is the smaller mass, the 8 kilogram mass. 37 degrees comes from the angle of our incline, which we know the angle of our incline is geometrically the same as this angle between the resultant weight and the y component of the weight. That angle right there is 37 degrees. And then our mu sub k was our given coefficient of kinetic friction between the 8 kilogram block and the surface as 0.23. If we plug all these numbers in, we find that the acceleration of our block in the x dimension, so along the incline, is 4.0 meters per second squared in the positive direction, as long as we define positive as up the incline. That is the acceleration of our entire system, of both the 8 kilogram block and the 16 kilogram block. Now, if we want to find the tension that's in the string that attaches the two of the blocks, let's look at the simpler object in order to evaluate tension. Let's look here at this 16 kilogram block in its free body diagram. If we look at the free body diagram of our 16 kilogram block, we'll represent the 16 kilogram block with a single dot. We have the weight of that block, and we have the tension of the block, the tension of the string that's attached to the block. This would be some of our forces in this perspective from the y dimension. We have tension and weight equals the mass times our acceleration. Tension is positive. Weight is in the negative direction. this acceleration in the y dimension is the same as our acceleration in the x dimension. Is the same as the acceleration in the x dimension that we found just previously, 4.0 meters per second. That's the rate at which the block, 8 kilogram block, is moving up the incline. It's also the same rate at which the 16 kilogram block is falling. So if we're trying to find the tension, then we can isolate tension by himself by moving weight to the other side. So now we have the weight of the block plus mass times the acceleration of the block. The weight is the large mass, 16 kilograms, times gravitational pull, plus the mass of our system, the mass of our block in this case. I'm sorry, this should be large M. It should be a large M. It should be a large M, because those are the forces that are acting on this block in particular. Large M. All right, so we get 16 times 9.8 plus 4, and our tension is 220 newtons. Because 16 times 9.8 plus 16 times 4.0 gives us the 220 newtons that we're looking for. All right, thank you.